Annenberg Media.
When I was a student in college, just as you are now, I took a course in modern history. And one day during this course, the professor said, "And that brings us to the end of the 19th century." Well, I timidly raised my little hand, and I said, "Professor, sir," we were very respectful in those days, I said, "Sir, you spent 2 weeks teaching us about the theory of 19th century warfare, and you never said one word about the theories of James Clerk Maxwell. Now, the theory of 19th century warfare is a matter of no lasting significance, while what Maxwell did affects every single day of our lives. Don't you think that that's rather a bizarre distortion of what's important about history?" I guess maybe we weren't always so respectful after all. Well, to his credit, he was embarrassed by my question. He did know who Maxwell was, and he briefly explained to the class what he had done. But the point is that the history of science is the stepchild of the historical profession. Most historians just ignore it because they don't understand it. They're a little like the fellow who searched for his keys under the lamppost because that's where the light is, even though he had lost them somewhere else. Well, I'll tell you what I'm going to do. I'm not going to say a word about the history of theories of 19th century warfare, but I am going to tell you all about the beautiful theories of James Clerk Maxwell.
Elegant mathematical theories weren't the only things of beauty with which James Clerk Maxwell surrounded himself. There were his precious books, of course, and outside his well-appointed study, there were the rolling hills of Glenlair, the Maxwell family estate, 2 days' journey from Edinburgh. And every morning, even nearer to his heart, there was Catherine.
Good morning, James.
Oh, you're a bloody lass. You brought me tea.
Yes, I brought you some tea.
They'd met in Aberdeen, at Marischal College, where he'd gone to teach in 1856. 2 years later, James wrote his Aunt Kay, "This comes to tell you that I am going to have a wife." He predicted that a new bride certainly won't stop mathematics. Characteristic of Maxwell's scientific predictions, this one proved accurate indeed. Of course, Maxwell wasn't the first to make accurate predictions about the deep mysteries of natural forces. 2 centuries earlier, Isaac Newton had written a book on the subject. But he'd had to express himself in terms of action at a distance. And that idea would come to be applied not only to gravity, but also to electricity and to magnetism. And then, in the 1830s, on the heels of the Frenchmen, Coulomb and Ampere, and especially on the trail of Hans Christian Ørsted, along came Michael Faraday. He'd been increasingly drawn toward electricity and magnetism, and by August of 1831, his path was reasonably clear. Picking up where Ørsted left off, Faraday confirmed that an electric current can produce a magnetic field. And then, going far beyond, Faraday demonstrated that a changing magnetic flux can create an electric current. And that a changing electric current in one circuit can induce current to flow in another.
Right, the Faraday book.
Thereafter, especially in light of similar discoveries by America's Joseph Henry, the principle of induction in the nature of electricity and magnetism was there for the scientific world to behold. And certainly within the Maxwell house, Faraday's experimental researches in electricity was considered the definitive text. But by the time he got hold of Faraday's work, Maxwell was ready to draw new conclusions, an ability which he developed early on. As a student at Cambridge, Maxwell's mathematics teacher observed, "It appears impossible for him to think incorrectly on physical subjects." Soon after that, as a graduate student, he wrote a paper that gave the scientific community reason to agree. It was called On Faraday's Lines of Force. And in preparation for that work, James Clerk Maxwell had done his homework. In the spring of 1846, Michael Faraday had penned a paper called Thoughts on Ray Vibrations. In that prophetic publication, he speculated that light is a type of vibration in the lines of force. The lines of force, he wrote, are known to connect particles and also masses of matter together. In other words, in Faraday's imagination, electric charges were linked together by lines of force in empty space. However, even though his idea was easy to see in the mind's eye, it introduced an intriguing scientific question. Would a vibrating charge set the lines of force into vibration? At this point, Faraday might have pictured each line behaving as if it were a linked row of mechanical oscillators. And in that case, he would have seen a disturbance propagate along the row, either as a longitudinal wave or as a transverse wave. But no matter how they might have taken shape in his mind, the significance of those vibrations was in the fact that Faraday had seen them. And somewhere between the lines of Michael Faraday's Thoughts on Ray Vibrations, James Clerk Maxwell would discover his electromagnetic theory of light. However, before he could read Faraday's handwriting on the wall to refine and polish it with his elegant mathematics, Maxwell needed to decipher a crucial clue. Within the forces of electricity and magnetism, he found a very significant speed. Any wave has a definite speed, depending on what makes it go. For example, in deep water, the speed of waves depends on the acceleration of gravity and the length of the wave. In air, the speed of sound depends on the air pressure as well as the density of the medium. And for linked oscillators, the speed is given by the spring constant, the mass, and the distance between oscillators. So it was time for Maxwell to get down to determining the speed of waves in Faraday's lines of force. From Maxwell's mathematical perspective, Faraday's lines were an expression of the 1 over r squared nature of the forces of gravity, of electricity, and of magnetism. At the same time, each of those has a specific constant. And in the right scientific hands, those facts got around to this. Since the fundamental forces of electricity and magnetism aren't independent, the electric constant, K sub E, and the magnetic constant, K sub M, should be related. But the question is, how? The ratio, K sub E divided by K sub M, has the units meters squared over seconds squared. In other words, the square of a speed. But what speed? Its square is 9 times 10 to the 16th meters squared per second squared. Divide the electric constant by the magnetic constant. And there it is, the speed of light.
Take your electrification by separating from...
It was an amazing discovery.
Now we can have a spot of tea.
After 50 years of the closest scientific scrutiny elsewhere, James Clerk Maxwell saw the light and found its speed in the forces of electricity and magnetism. But the fundamental forces weren't all that occupied Maxwell's mind. Around 1857, an academic prize was offered to anyone who could explain the solid nature of the rings of Saturn and their steady movement around the planet. Maxwell's answer was right on the mark. The only structure that could account for such stability, Maxwell wrote, was one made up of clusters of disconnected particles.
Those in which there is electrification.
Maxwell's essay not only won the Cambridge Prize, it won the praise of the scientific community at large. Sir George Airy, Britain's royal astronomer, called it a most remarkable application of mathematics. Perhaps because one good turn deserves another, Maxwell immediately set his sights on moving particles other than those of Saturn's rings.
Along a given path.
He developed a kinetic theory of gases in which gas molecules are small, elastic particles that collide with one another as they move about with various velocities. Maxwell believed all physics research should advance on, in his words, strict mechanical principles. That belief led not only to Maxwell's theory of gases, it led to his great accomplishments in electricity and magnetism. To pursue his research, the Maxwells moved to Kensington, London in 1860. For 5 years at King's College, he was productive in kinetic theory and electricity alike. And here at London's Royal Institution, Maxwell finally met Faraday. Faraday, remember, had seen electricity in mechanical terms, not merely as an idea in keeping with Newton's action at a distance, but as a thing of physical lines, a solid structure of force that radiated through space. Maxwell would state with great admiration that Faraday had seen a medium where the strict Newtonians saw nothing but distance. Perceptively, Maxwell added that Faraday sought the seed of the phenomena in real actions going on in the medium. Of course, as it would later be seen, the medium is the electromagnetic field, and that's where the action really is. But before Maxwell could get the message from the medium, he had to determine whether waves could travel through the electric and magnetic fields at the speed of light. If so, they would have to obey the 4 laws of electricity and magnetism.
The electric flux through any closed surface is equal to 4 pi k sub e times q, or q over epsilon naught, where q is the total charge enclosed by the surface. And the magnetic flux through any closed surface is always equal to 0. These are Gauss's laws for electricity and magnetism. The circulation of magnetic field around any closed path is equal to mu naught times the electric current passing through that path. This is Ampere's law. The circulation of electric field around any closed path is equal to minus the rate of change of magnetic flux through that path. This is Faraday's law of electromagnetic induction.
So suppose that there can be a wave in the intensity of the electric field. This one's a transverse plane wave, and it travels, of course, at the speed of light. But consider the field at any one instant. Since it's up in one region and down in the next, it has a circulation about this path. According to Faraday's law, that means that there must be magnetic flux through that same path, and furthermore, that it must be changing in time. And that can only mean one thing. A magnetic wave must tag along with the electric wave everywhere it goes. But, and here's the crux of the problem, that in turn means at any instant there's a circulation of the magnetic field about this path. And according to Ampere's law, that can only be true if there's current flowing through it. But in empty space, there's no matter and no electric currents. So there's no way around the fact that according to the laws of electricity and magnetism in Maxwell's time, there could be absolutely no electromagnetic waves in space. The point was this: if the laws of physics stated that waves couldn't exist in empty space, could it have been that, as fundamental as they were, those laws were somehow incomplete? Maxwell's task was to examine the fundamental laws of his era, and his triumph was to find the missing piece. And he did so, by looking into a simple and altogether conventional apparatus, the capacitor. The magnetic circulation around any path depends on the electric current linked through the path. The only way to be sure that the current goes through the path is to imagine a membrane bounded by the path. Then the same current must pass through the membrane, no matter what shape the membrane takes. But that's no longer true if the current flows into a capacitor. Then, even though current is flowing, there may be none through the membrane. If so, what is the magnetic circulation equal to? Seeking an answer to that question, Maxwell took a page from Faraday's book. Changing magnetic flux creates electric circulation. And then, as usual, he looked at things the other way around. Could changing electric flux, he wondered, create magnetic circulation? The answer promised to solve the capacitor problem.
As current flows into the capacitor, charge builds up, which creates an increasing electric field between the plates. The electric flux through the membrane can be deduced from Gauss's law by imagining a closed surface. All the flux goes through the dome-shaped membrane, and it's equal to the charge on the capacitor plate over epsilon naught. The rate of change of electric flux can be found by differentiating both sides of the equation. It's given simply by the current flowing in the wire. In other words, epsilon naught times the rate of change of electric flux through the dome-shaped membrane is the same as the electric current through the flat membrane.
This was Maxwell's crucial discovery: the precise manner in which changing electric flux can generate a magnetic field as if it were a kind of electric current. In fact, Maxwell himself called this mathematical term the displacement current. In other words, the magnetic circulation around a closed path is given not only by the electric current through it, but also by the rate of change of electric flux through it. This was how James Clerk Maxwell completed the laws of electricity and magnetism. And with these laws, Maxwell could show that electromagnetic waves of every frequency and wavelength would propagate through empty space at the speed of light. Maxwell's discovery, which seemed purely theoretical at the time, would lead to the sights and sounds of the 20th century, radiating through space not only as visible light, but also as radio waves, microwaves, and the entire electromagnetic spectrum. It was a discovery that would lead far beyond the Earth into the deepest reaches of space, where a wave in the intensity of the electric field implies the existence of a changing magnetic flux. That means a wave in the magnetic field. And that's made possible by changing electric flux. And it's made clear only because Maxwell understood that electric and magnetic fields create each other if they move in a wave together at the speed of light. And so it goes, in lockstep through eternity, both fields propagating throughout the universe. And in that light, always at the speed of light, one can finally see the power and the glory of Maxwell's equations. Just as Newton was born the year Galileo died, Maxwell was born in 1831, the year Faraday discovered electromagnetic induction. And he died in 1879, the year of Albert Einstein's birth. What could be more fitting? For between Newton and Einstein, no men in scientific history made a deeper mark. Maxwell went ahead to refine and redefine the fundamental laws of nature, and in the process, to build a bridge to modern physics.
The fact is that Maxwell was endowed with one of the finest minds that the human race produced during the 19th century, and that, combined with his superb Cambridge education, made it possible for him to do absolutely anything he wanted to. I haven't told you about his sense of humor, although once, a long time ago, if you remember, I read to you one of his comic poems about the Atlantic Telegraph Company. Well, I would like to read to you a little bit today from another one of his comic verses. The poem is in this book, which is very old and rare and valuable, and I don't want to handle it too much in class, so I'll just tear out a few pages so that I can read it to you. This is a homework problem, and in the first verse, he sets out the problem. An inextensible heavy chain lies on a smooth horizontal plane. An impulsive force is applied at A. Required, the initial motion at K. What he's talking about is there's a chain lying on a table like that, and somebody jerks it at one end, and the question is, how does the other end of the chain begin to move? That is absolutely typical of the kind of extremely difficult and utterly useless problem that Cambridge students have traditionally been trained on. Well, having set out the problem, he then shows us how to solve it in great detail. So I'll tell you what I'd like you to do. I'd like you to go home tonight and work out your homework problems in verse and bring them back with you that way when you come here next time. I'll see you then.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.